So I wanted to give another example of a one-dimensional force problem. In this one, the difference is we have to think about that there are forces not just acting in the dimension that we really are caring about. So I thought this would be a decent example. As in all these problems, the first step is to draw a free body diagram. And if we think about what forces are acting here, we know that gravity is pulling it down. And there's a normal force pushing it up. And it says that the student is dragging the box across the floor. So we'll say F pull. And it says there's a frictional force back the other way. So I feel like the thing that students are asking about is which of these forces actually go into my sigma F equation. So in general, we're going to see that there are forces in the vertical dimension, which we call y, and in the horizontal dimension, which we call x. And you only have to deal with one of those dimensions at a time. In fact, if we were going to be dealing with both of them, we would solve two separate problems, one for each. In the problems you're going to see in this first unit, one of the dimensions will always have a net force of 0. So for example, in this problem, normal and gravity entirely cancel out. So once you do your free body diagram, you should really ask yourself, what dimension is this caring about? This problem I showed you previously, that was the y dimension. This one is the x dimension. So let's go ahead now and write sigma F equals ma. And again, we're just worrying about x forces. So I see FP minus FFR equals ma. So as we go to solve it, we can plug stuff in. We don't know FP. The force of friction here is 50. And the mass of the box is 43 kilograms. And we don't know A. So I like to start really with the free body diagram sum of force equation. Sometimes that's not solvable yet because now we hit two unknowns. So then we just go back to our motion equations and solve one of them to get acceleration. So I guess I should look at the rest of the problem. I see 2 meters and I see 0.75 meters per second. 2 meters is my final distance. 0.75 meters per second, that's how fast it's going by the end. So that's my final velocity. We could probably guess a couple other things. We could probably guess that we're starting at position 0. And it says starts at rest. So that means we have a VO of 0. All right, so let's solve. If I've got x's and v's and notably not times, then this is the equation I'm looking at. That's the easiest one to use. So I'll go ahead and write that. Again, I always write my equation first. That helps me to not plug in incorrectly. It also gets me partial credit on a test if I do everything else wrong at this point. At least I picked the right equation. So 0.75. .75 times 0.75, 5625. That equals 4a divided by 4. So 0.141 meters per second squared is A. All right, so now I can sub in. So I get FP minus 50 is 43 times 0.141. So FP minus 50 equals 43 times 0.141. 6.063. Now we add 50 to both sides. So 56.06. And that's it. So big difference in this problem. It's a horizontal problem. We can ignore our vertical forces because they, first of all, are in a different dimension and don't affect horizontal motion. But second of all, in this unit, they will cancel. So we're just left with our horizontal forces. Again, when you don't have something solvable because you don't have acceleration, that means you go do a motion problem. You should be able to do it. This is the trickiest thing we've done so far this year, and it's one of the trickiest things we'll do this year. With some practice, you'll be okay at it.